discuss about Newtonian formulation. Why Newtonian formulations are required? So first we have to know generalized coordinate, or first we have to discuss about degrees of freedom. What is the degree of freedom? The number of total independent quantities required to describe a dynamical or a static system, that is called degree of freedom. That means if we consider one particle in 3D space, so we know that it can travel along x direction, or it can travel along y direction, or it can travel along z direction. So we can get the particle velocity in x direction or y direction or z direction. So basically the degree of freedom of a single particle under 3D space should be equal to 3 for a single particle. If we consider n number of particles, then we can get 3n. The degree of freedom will be 3n. For 3 particles, there is no interaction between 2 particles. That case, we can get degree of freedom equal to 3. If we consider the particle exists in a plane, then what will be the degree of freedom? So it can get along x direction and it can get along y direction. So we can get we need 2 coordinates to describe one dynamic or static system. So degree of freedom will be 2. And for n number of particles, you can see that the total degree of freedom will be 2n. Now, if we make some consideration such that one particle is moving along a circular track in xy plane, then what will be the number of degree of freedom? We know that here also we know that the particle to describe the particle motion we require 2 coordinates x and y, but we can reduce the number of coordinates. How? Now here we know that the radius of the circular track is constant, so r equal to a. So if we transform the coordinate system from Cartesian to polar, so there we can get new coordinate system in another space r and theta. So if we go for Cartesian to polar, if we transform to Cartesian to polar coordinate system, then we can get that r and theta, and here we know that r equal to constant. So if we describe every point of the circular track, that will be a theta 1, a theta 2, a theta 3. Basically we can get one. So here one coordinate is sufficient to describe this motion. So the degree of freedom of that case will be 1. So in this way we can reduce the number of coordinates that required to describe the motion of the particle. So this is basically degree of freedom. So we can say that the degree of freedom, or f, will be equal to, for 3D case, if there is no any interaction or no any boundary condition, here we consider that the particle is bound along a radius r equal to a. So here one boundary condition is there. If we impose new number of boundary condition, then we can get degrees of freedom will be 3n minus mu. So here mu is called constraints. Constraints is basically that opposed to the motion of a dynamic system or of a dynamic particle. So the degree of freedom for new number of constant, we can get 3n minus mu. So in this way we can reduce the number of independent coordinates required for description of dynamical system. Now we will discuss about Lagrangian formulation. Why Lagrangian comes? Actually, we can deal any classical system, any classical mechanics or any classical system using Newtonian mechanics. But problem arises when the number of particles are very large. And another, that is one case, and second case is if the system is very complex, that means we can consider one double pendulum case, means one pendulum at rest and another pendulum is attached to the end of the first pendulum. So if we want to make the equation of motion of these two particles m1 and m2, so if we use the Newtonian mechanics, so some complication will be there. So to remove this complication or to make it simplify, we need Lagrange or Lagrangian dynamics. So this is the basic benefit for the Lagrangian. And another problem is, if we take lot of particle, so here the motion of the system will be like for number 1 particle, it can go that direction. So from Newtonian mechanics we can calculate that F1 equal to m1 into a1, F2 equal to m2 into a2. So for n number of particles, and we know that for 3-dimensional case, we know that every particle has 3 independent coordinate. So we need basically 3n number of equations if there is no any restriction between them. But in general case, we know that there has some interaction. So the number of equation will be, if number of degrees of freedom, so it will be 3n minus mu. If mu is constant, then we can say that n is the degree of freedom, or in number of equations are required to describe this. We have to solve this equation, then we can get what will be the dynamical nature of this system. So that is very time consuming thing and very difficult thing. So we can use generalized coordinate to replace this f number or n number of equation. We can use generalized coordinate. What is generalized coordinate? We will discuss later. Third problem is, for Newtonian mechanics, we have to deal with the force, and sometimes we know the effect of the force, but what is the amount of force, but which kind of force involved in the dynamic system, that we don't know. Or to get the solution of this equation, we have to know all the nature and behavior of the force. So sometimes we don't know about that. So for this complexity, we can remove using Lagrangian dynamics, because in Lagrange we deal with energy of the system, kinetic energy and potential energy of the system, kinetic energy T and potential energy T of the system. So these are the basic benefit. That's why we use Lagrangian dynamics rather than Newtonian for a complex system. Now we have to discuss about the generalized coordinate. Generalized coordinate. Actually, for a complex system, or if the number of particles are very large, that kind of system, we require to solve lot of equations and these equations are made of lot of coordinate. To remove this coordinate or to replace this coordinate, we can put a single coordinate, that is called generalized coordinate. That means we can say that we assumed a generalized coordinate as r. R is the function of q1, q2, q3, q4 and time. So within we know that for a complex system, or where the number of particles are very large, for that case we have to solve lot of equations. To construct this equation, we need lot of coordinate. To replace this all coordinate in a single coordinate, that is called the generalized coordinate. And if we make the generalized coordinate, then we can easily solve any complex problem in a classical mechanics. So that is the basic benefit to use the generalized coordinate. So here, what is the basic nature of the generalized coordinate? Means it can be constructed any kind of coordinate, not necessary that all the coordinates should be the equal dimension of length, or so q1, q2, the dimension of q1, q2 will be different. Maybe q1 represents position x, q2 maybe represent x dot, that kind of thing. And also the last coordinate should be the time. So dimension of all the constituents of generalized coordinate, it it is not necessarily the dimension of length, so it can different dimension. Now if we derive it with respect to time, what will be the result? Del R del T should be equal to, so R is dependent on lot of coordinate q1, q2, q3, qn, so we can say that dr dq1 dq1 into dq dot dq1 dot plus dr dq2 dq2 dot. So we can represent this like that. So we can write this summation over I del r del qk into dqk dot. We can represent it like that. So it gives the velocity. We can write it d. So if we derive it again with respect to del qk dot, it will give summation over I del r del qk. So that is the basic relation of generalized coordinates. Now we have to understand the virtual work done. What is a virtual work? So we know that from the Newton's equation, F equal to m into r dot. But what is the nature of the force? The force is equal to F plus R. What is F and what is R? We already know that for a complex system or a rigid body problem, so we can consider it can be created, or it has lot of atoms or particles inside the matter. So if we consider the equilibrium position or equilibrium condition of that system, so we know that for the equilibrium condition, or especially for the mechanical equilibrium condition, we know that summation over Fi equal to 0. So we have to specifically we have to sure that the force acting on the particle, on the constituent particle of this matter, should be equal to 0 at a particular time. At a particular time, the force acting on the constituent particle of this matter should be equal to 0. But we know that the particles under or inside the system are made of some atoms, and we already know that atoms are made of electrons, so it has some motion. So the force will not neutralize. So if we want to make a system stationary or with equilibrium condition, if we make a equilibrium condition, so how the equilibrium condition are established? Already a stable matter, we can see that lot of interactions are there. Using this interaction, after summation of this interaction, we can get this summation over Fi equal to 0. But at a particular time, if we see this particle has motion, this particle has motion, so if we deal of the mechanical property or the mechanics of this system, so we have to get the solution of the equation of each individual particle. That is very difficult. That's why we can consider that how much coordinates are required or how much equations are required to solve this problem. So we already know that if there has some interaction, so we will get F number of, we have to construct, or we will get F number of equation, and we have to construct F number of equation to describe this phenomenon. So F equal to 3n minus b. So this can be replaced by generalized coordinate. So So to remove this number of constants, or to remove this number of equations that restrict to solve the whole body problem, we can consider that or we have to give some force. Means if we provide some force react with this problem, some force will react with this problem. That means it reduces, or it has the power, it can vanish all this constant force. So at a particular time, so the work done by this force should be equal to 0, because that is happening for a particular time moment. So work done by that force, summation of R into del R should be equal to 0, because it happens without allowing some interval of time. So the work done due to this force will be 0. This phenomena, or this thing, is called virtual work done. Why virtual work done required? Just to remove the constant force, to remove this constant force or that number of equation, we need this virtual force or virtual work done. That is the concept of virtual force or virtual work done. Now we have to study the D'Alembert principle. What is D'Alembert's principle? We know that total applied force equal to F plus R, where R can reduce the constant force of motion, and F is called dynamic force. F is called dynamic force. So F equal to F plus R, and according to D'Alembert's principle or D'Alembert's theory, we can show that, or according to D'Alembert's principle, del of virtual work done within a system should be equal to 0. So R, for a equilibrium condition or equilibrium system, we can show that del R should be equal to 0. So what will be the equation of motion? So now the equation of motion will be F dot del R equal to Fi F plus R del Ri equal to 0. So this will be equal to summation over E dot del R. The rate of change of momentum of individual particle to del R should be equal to 0. So, and already we know that this part will be 0, so we can construct the equation F minus E dot del R should be equal to 0. That is the D'Alembert's theorem. Summation over I Fi minus Ei dot del R will be equal to 0. Now we have to know some conditions. Holonomic. First one is holonomic. Holonomic system. What is holonomic system? If we construct one generalized coordinate H is the function of position and time, and if we construct some equation using this generalized coordinate, that means L or K, L equal to the function of H, then we can tell the system is a holonomic system. What is non-holonomic system? Basically, we can represent H as A I L R plus A I J K L into E T. We represent H as this one. If we can differentiate it, or if H has some particular value, then we can tell that H can be integrable. H can be an integrable function. If H is equal to 0, then we can say that this function is not integrable function. So that is the condition. Using this condition, we can know the behavior of the system. Either it will be harmonic or it will be non-harmonic. And another two system is scleronomic and geonomic. If it is dependent on time, then it is called scleronomic, and geonomic, if it does not depend on time, then we can call it geonomic. So now we have to construct the Lagrangian using the D'Alembert's principle. The D'Alembert's principle means summation over I Fi minus P dot del R equal to 0, R equal to 0. So we can write summation over I Fi del Ri equal to summation over I Ei del Ri. From that, we know that, or we can represent it. So Pi dot del delta Ri can be represented as del Ri del Qk into dqk. So we will put this condition del Ri del Qk into dqk. Here also we can put Fi into del Ri into del Qk into dqk. If we see that equation, we can write it into Vi dot or del Vi del T del Ri del Qk dqk. It can be represented as summation over m into, and we know that if we put common del of T, it will be m del V this one minus m Vi del Ri dot del Qk inside here. Then we can write that I m del T of, or dt of m Vi del Vi or del Qk dot, because we already know that del R del Qk equal to del V del Qk dot. So minus summation over m minus summation over m Vi del Ri dash del Qk. So it will give summation over ddt of del Qk dot half of m Vi square minus summation over, it will give m Vi del Qk. So from this equation we will get ddt of del Qk dot half of m V square minus summation over I del of del qk half of mvi square. That is the right hand part. What will be the left hand part? Left hand part is equal to fi into del r del qk into dqk. Now this part, summation of our fi del r del qk, that is called generalized force. Why that is called generalized force? Actually, if you see that the dimension wise it represents the force, but it can represent all the effect of all the coordinates using this qk. That's why that is called generalized force. That means it does not indicate any individual, rather than it represents the summation of all individual forces. So that is called generalized force, that represented by qk. And then what will be the, if we equate this, summation over d dt of del qk dot half of m square di square minus summation over, or if we take this thing over this, del r is there, del qk is there, del of del qk half of m di square, del qk should be equal to summation over qk dqk. That is the generalized equation of the Lagrangian formulation. But if we reduce it more, then what we can get? We know that half mv square and half is the kinetic energy of the ith particle. So we can write that del dt of del qk dot t minus del of del qk t del qk equal to del f del qk into dqk. F into del r del qk del r into dqk. And we know that if the system is conserved, then we can represent F as gradient of potential. So F can be represented as minus del V del R I. So if we put here, then we can get minus summation over del V del QK dQK. And we already know that this potential does not depend on velocity, of the particle. For a general case, if we consider velocity does not depend on the velocity, potential does not depend on the velocity of the particle, then we can describe as del T minus del V del QK dot minus del T minus V into dQK del QK equal to 0. dQK will be equal to 0. So from this equation we can tell that if we consider T minus D equal to L, then ddt of del L del QK dot minus del L del QK will be equal to 0, summation of I. This equation is called Lagrangian equation or Lagrange-Euler equation. So how can we get Newton's formula from this equation? Now we know that Lagrangian has T minus V, Lagrangian equal to T minus V, but V is not the function of QK dot. So we can write the first term as ddt of del T del QK dot will be equal to del L del QK, and we know that for the kinetic energy equal to half mv square. So it depends on velocity, but it does not depend on the generalized coordinate or any coordinate. So this gives minus del V del QK. That means that gives the force F plus F, and that side if we differentiate it, we can get T equal to half in di square ddt of del QK dot. If we differentiate it, we can get in del V del V del T equal to F in del V del T will be equal to F. So in this way we can get Newton's formula from the Lagrangian formulation.